Now I'd like to look at another example using integration by parts. And the reason I want to look at this is it operates in a way that's a little bit unorthodox. Most of them will not happen this way. But in the case where you have an exponential times sine or an exponential times cosine, a very interesting thing arises. So let's think about how we would proceed here. So remember, our first thing is trying to decide what makes sense as our u and what makes sense as our dv. Now, immediately you might see why this is a unique situation, because differentiating that exponential doesn't really get any simpler, and integrating it doesn't get any more complicated. So seems to be no preference for where that goes. Sine, differentiating sine just leads to cosine, so not any easier or harder. And integrating sine leads to cosine. So not really any easier or harder there either. So it doesn't seem like there's really any benefit to either location. It may also make you think that we shouldn't even do integration by parts. And that's why I want to look at this example, because it's very easy to convince yourself that maybe this isn't the right technique. So really, we can start off any way we like. I'm going to put the trig function as u, but really there's no benefit either way. So they work out the same amount. So I'll do the sine as my u and the exponential as my dv. So du, we do have a little bit of chain rule going on here. So 2 cosine 2x dx. And then here we've got the little bit of u sub going on there. So 1/3 e to the 3x. So using our formula, this is uv, 1/3 e to the 3x times sine 2x minus the integral of v du, 2/3 e to the 3x cosine 2x dx. And so right away you think, well, maybe this isn't the right approach. I started with an integral involving an exponential and a trig function, and now I have an exponential and a trig function. And all I've really accomplished is picking up a constant. So it doesn't seem to be progressing. But let's blindly plow forward here. Now, I said it doesn't matter what was u and what was dv, same amount of work either way. But once you've committed, you want to stick with that. So I had trig function as u, so I'm going to do trig function as u again. If you switch midstream, essentially all you're going to do is undo this work, because you're going to reverse these processes. So since I did trig function there, I'm going to do trig function again. So, and the 2/3 could go anywhere. I'll just put it on the u. So 2/3 cosine 2x for my u, and e to the 3x dx for my dv. So over here, du, when I differentiate, I'll pick up a 2 from chain rule. So 4/3 negative sine 2x dx. And here, by u sub, linear u sub, I pick up a 1/3. So let's now apply our formula to that and see what we have. So we have the original uv from our first time through, then minus uv, which would be 2/9 e to the 3x cosine 2x. And then, and just so I don't get lost with my minuses, let's save the distributing of that minus for after the fact. So uv minus the integral of v du, and there's a minus in that, right? So minus a minus is going to make that plus because of that minus right there. And we're looking at 4/9 e to the 3x sine 2x dx. Okay, now, seems even worse, right? We started with an exponential and sine. We went through all this work, and we still have an exponential and sine. So this seems to have been a complete waste of time, but it's not exactly this integral, right? It's some constant multiple of this integral. And now what I want to do is think of what we have here as an algebra problem. So what do we have? On one side of this equation, we have our integral. Through a series of equalities, this integral is equal to all this. What I'd like to do is take this final integral here, which when I distribute the minus is going to be a minus there, and add it to both sides of the equation. So let's, just as a shorthand, let's give this integral a name. I'll call it capital I. So I'm going to, just so I don't have to write it every time, I is the integral e to the 3x sine 2x dx. And the equation we have currently is that I equals this minus this, and the distributing the minus, so 1/3 e to the 3x sine 2x minus 2/9 e to the 3x cosine 2x, and then distributing that minus 4/9 of that integral. So I'm just going to say minus 4/9 I. And what do we want to know? We want to know what is this integral equal? What is I? Well, now we have a little algebra problem here, and we want to solve for I. So I'm going to add 4/9 of this integral to both sides. Well, I have 1I plus 4/9 I be 13/9 of I. And now there's no integrals left over here, so I am going to finally write plus a constant. Now we're not quite done. What did we want to know? We wanted to know what is I. What does this integral equal? Well, 13/9 of that integral equals this. So let's multiply by 9/13 on both sides, just like we were solving an algebra equation for I. So it's 9/13 times 1/3. Well, just leave it out front there. And there we have it. Our integral, which we were interested in, what does that integral equal? It equals this. So this idea of doing integration by parts twice, ending up with an integral that's just some multiple of your original integral, and then using this sort of algebra approach to solve for it, is a little bit unusual. It doesn't come up really for us in this section other than in the situation of an exponential times sine or an exponential times cosine. And if you think about it, you can see why that's true, because what made us end up back where we started is the fact that the exponential doesn't go anywhere, right? You just keep integrating that, and you'll just have multiples of e to the 3x. And if you differentiate sine twice, you're back to a multiple of sine. So, or if you differentiate cosine twice, you're back to a multiple of cosine. So it'll work in those situations. Later on, we will see another situation when we start looking at integrals of various trig functions where this comes up again. But for right now, it's in situations where you have an exponential times sine or an exponential times cosine.